Okay, in this video, let's do some proofs. We're going to do the existential elimination. Let's do a couple of problems that require the use of existential elimination. So, before we do so, existential elimination is our last, or rather our fourth discharging rule. Um, it's a rule where if we use it, we're going to need an assumption, and once we use it, we discharge that assumption. So let's start off with this argument right here. It says that our premise is there exists an x such that x is g. Therefore, for all x, there's a y such that if x is f, then y is g. Okay, so first off, we have an existential premise, right? And the key here to existential elimination is understanding that we actually can't use this premise. Like we can't say that because something is g, we know for sure that an instance of it, say a is g, is true. So what we have to do is actually assume this instance in order to work with it. So we assume an instance of it, of our existential, in order to work with that specific instance. And so here our note says that we're going to eliminate this assumption with existential elimination, right? And so we go on to make another assumption. So here our assumption is B is F. We're doing this for two reasons, right? First off, B, right, is going to matter later on, as we'll see. We can't assume A. The other reason is that we need to get F somehow, right? And so if we know that the consequent is true, then we can assume whatever we'd like for the antecedent, use arrow introduction to discharge the assumption immediately. So on the next line, we'll see that this happens here, right? With the assumption that A is G and B is F, we can say that if B is F, then A is G, using lines 2 and 3, arrow introduction. Because arrow introduction is a discharging rule, we immediately discharge line 3. So line 4's dependency number only has 2. Okay, so from there we move on to line 5. Here we change this conditional into an existential sentence. We do so by using existential introduction. The existential introduction replaces the constant a with a y, right, first. So because our conclusion is a universal, we're going to have to use universal introduction last, because this is the main connective, and this is the connective that is within the scope of the universal sentence. Okay, so after that, like I said, we're going to use universal introduction on line 5 so that we get the universal sentence. Now, we do the universal introduction from B here, we change into an X, right, and place the universal quantifier. Because we do so, remember that the one restriction that we have for universalizing, or rather using the rule of universal introduction, is that this constant b, right, cannot occur within the dependency numbers on the line with which you're trying to universalize. So we're trying to universalize 5, so b should not be in 2. And because 2 has a, we're safe to do so. See, if we were to assume a on 3, we would run into the problem of universalizing from 5. If this were a, we'd have to check to see if it would be in 2, and of course the a would be in 2, so we could not do a universal introduction were we to assume that a is f. So that's why we assume that b is f. Okay, so on line 7, because our dependency number is 2, and that's an assumption, we cannot end the proof here. So what we need to do is discharge that assumption with existential elimination. So the way to use existential elimination, right, is we need three reference numbers, right? The first being the original existential sentence, the second being in the assumption of an instance of that existential sentence, and lastly, the target formula with which we are repeating. Here, existential elimination says that we can get to this formula, right, from any instance whatsoever. So here, if we change this, this would be an arbitrary instance. We can get to this formula without actually requiring that A be G. So there are three restrictions with which we put into place to make sure that existential elimination works out correctly. And if you remember, the three provisos that are included sort of mirror or match up with the three reference numbers that we have to have when we cite the rule. So the first one, if we look at our target formula, our assumption of the constant A cannot occur in our target formula. So A cannot occur anywhere here. It doesn't, so we're fine. The second restriction, right, has to do with whether or not A occurs in the dependency numbers of our target formula. So we have to make sure that A does not occur in the dependency numbers on this line. A does occur in 2, but the restriction, of course, allows this as an exception. A can only occur in the dependency numbers if it's the assumption of the instance that we're doing. Right? That's the only exception. If it occurs anywhere else, then we've run into a problem. Okay, and lastly, A, right, the constant A must not occur in our original existential sentence. So here's our original existential sentence. A does not occur here, so we are safe to use existential elimination. So with existential elimination, our dependency numbers should be from 1, 2, and 6, and because 1, 2, and 6 have 1 and 2 gets discharged, we are left with 1 as the dependency number. Okay, so that's the gist of a straightforward, sort of straightforward, short-ish proof using existential elimination. Okay, let's do a longer proof of existential elimination. Here, let me write down the whole argument. It's okay. So there, oh, we've got two premises, I'm sorry. It's comma, right, for all x. So with the two premises, we can conclude that there is something that is f. So there's the full argument, right, or the full sequent. There exists an x such that x is f, or x is g and h. For all x, x is not g, nor is x h. So with the two premises, what we're going to do is, of course, look at them for a little bit and see what we can go from there. So here, remember, this is an existential sentence. That's the main connective. So we can't do much with this. However, our second premise is a universal sentence. And with universal sentences, of course, we can use universal elimination. So in order to use our existential formula, we're actually going to have to assume an instance of it. right? And so here we're going to assume an instance of it for existential elimination. Right? And the dependency numbers, of course, match the line numbers. Right? And then we're going to use universal elimination on line 2. Now that we've got these two formulas to work with, we can go ahead and start to move along in the proof. However, these two formulas are both disjunctions. And disjunction, of course, works very similar to existential elimination, where if we're going to use a part of it, we must assume that and try to derive some target or some formula that we're looking for. Here, if we assume the left-hand side of our disjunction on line 3, it's FA. Right, so here we assume it for OR elimination. However, if A is F, right, we know that something is F. Right, and that's just existential introduction. That should be EI. Right? If A is F, then we know something is F. If a particular object is F, then we know that something is F. Right? But this is our conclusion. So from here, that could be our target formula. It should be our target formula. Right? And so now what we have to do is try to show that from the other disjunct, we can also get to the same formula. Right? So here, this is the other disjunct, which we're going to assume, again, for OR elimination. Right? So that's line 7. Okay, so we move from there to doing a reductio. So we're going to assume the opposite of what we want, which is something is F. We're going to say that nothing is F, right? And so if we assume that nothing is F, we're going to get a contradiction with which we can use to negate this formula. Right? And then from there, if we assume, or rather take from this formula on 7 that A is G from and elimination, right, from 7, we're also going to find a few contradictions. Here we'll start to use this sentence that comes from line 2. So not GA, although is actually an assumption for OR elimination, because we want to use this this sentence here on line 4 to produce a contradiction. So as you can see, this will produce a contradiction with this, and this will produce a contradiction with this. So at any rate, if one of these were true, which it is, one of them must be true, it's going to give us a contradiction. So we're going to try to show that. So here on 10, what happens is we assume the left-hand side of this disjunction, right? We're going to get our contradiction. And then this from 9 and 10, negation elimination. 9 and 10 and 7 and 10. Right? And then we're going to do a conjunction elimination on 7, right? Just like we did here. And produce another contradiction by assuming the other side of the disjunction. Whoops, that's an assumption for OR elimination, right? And that's 13. And so we have another contradiction from 7 and 13. So that's 12 and 13, negation elimination. I was ahead of myself there. Okay, so we got a contradiction from the left-hand side of the disjunct on 4, and then we also got another contradiction from the right-hand side of the disjunct on 4. So either side of this disjunction, we get a contradiction. So now we repeat that contradiction on 15 and signal that we can get it from either side of this disjunction. So from 4, if we assume 10, we're going to run into 11, which is our target. And then from the other side, from 13, right, we're going to run into another disjunction, another contradiction. And so with OR elimination, we can take away or discharge these two assumptions. That is the one on 10 and 13. So here, our dependency numbers should be included. It should include the dependency numbers from line 4, 10, 11, 13, and 14. But we don't include 10 and 13. So we have 2 and 7. Right? And then from there, we can then discharge an assumption. Here we're going to discharge this assumption. Right? So we're going to use 15 and the assumption on 8 with negation elimination. Negation introduction. Right, negation introduction. So that we can negate our assumption to produce our conclusion. So there we have other dependency numbers from 15 and 8, but we don't include 8 because 8 gets discharged. So again, it's 2 and 7. Okay, now we can use double negation to produce the formula something is F. Okay, so now we have something is F, right, from 2 and 7, which 2 is our premise, and 7 is GA and HA, which is the other side of this disjunction. And then we also got there exists something that's F from this side. So what we did was we got something is F from the left-hand side of this disjunction on 3, and we also got it again from this, we got this formula again from the assumption on its right-hand side, GA and HA. Right? So that means we can repeat the formula and discharge these two assumptions, right, on 5 and 7. Okay, so we do that with OR elimination again. So what we do is we list the original disjunction, which is on 3, the left-hand side of its, which is FA on 5. Then we go to its target, which is 6. Then the other side, which is 7. And then finally, all the way down here, the target, 17. Okay, and that's OR elimination, right? I'll move up a bit. Okay, so once we do the OR elimination here, what we're discharging is 5 and 7, right? So what we get are dependency numbers from 3, 5, 6, 7, and 17. Of course, that's going to be 2, right? 3, but 5 and 7 do not get included. So that's 2 and 3. Okay, so finally, since we have 3 here, 3 is our assumption that we're going to discharge with existential elimination, which now we have to do. So on 19, right, we have to discharge with existential elimination, saying that if we assume an instance of our existential sentence, which is our premise, from 1, this assumption can produce this formula. So from 1, right, the assumption on 3 and the target 18, we can use existential elimination to discharge the assumption on 3. So the assumption on 3 no longer is included, and the dependency number should be from 1, 3, and 18, which is just 1 and 2. So there you have it. Now we've gotten to our conclusion, but our premises are the only ones that are included in our dependency numbers. And so the long-ish proof is done, right? So this is a pretty straightforward way of doing it. It's a pretty complex proof, but it's not bad. It's not too tricky. We can see that things fit together just fine. It's just that we have an existential, which produces a disjunction, and a universal, which also produces a disjunction. So we have to do a lot of disjunction eliminations, which take a long time, but they're pretty straightforward if you take a step back and look at them. So you've got this video. Hopefully you can study, pause, and help you through with some strategies on how to tackle complex proofs. Okay, thank you.